Well, good afternoon, everyone. As you can see, I will be talking about asymmetrical copulas and rainfall downscaling. Some of you who've been to EGU actually may remember this title. I've presented something, with a similar title at least, at EGU, but that was mainly about the fitting of these copulas, about their actual method. And here I'm going to discuss some preliminary results for the copulas we fitted between various scale levels. I've worked on this together with my promoter, Nico Verhoest, and our math advisor, Bernard Baats. First, I think it's important to stress that we focus on downscaling for medium to small scale hydrological modeling. So we're talking about a core scale here of about 5 kilometers by 5 kilometers for a single pixel, all the way up to, here in this presentation I will go all the way up to about 20 kilometers by 20 kilometers. And we go down to a scale of 500 by 500 meters, so that can be pretty small. Actually, of course, we want to do this without knowledge of our fine scale. And furthermore, this is based on radar data, so we take actually only the inner 100 kilometers. We synthetically aggregate this and then fit a copula in between and investigate the relationships we find. This was taken from the Belgian Royal Meteorological Institution at Wiedemont, and the reliable range is actually it's 100 kilometers. Of course, the first question we may have is why use copulas at all in downscaling? Well, first, I think we have to discuss fractal methods. They're very parsimonious. You'll usually have only a few parameters, all the way down to 1 actually for the Hurst-Kolmogorov methods. They're also very effective at producing various statistics of rainfall. However, they can be very difficult to estimate and also very difficult to extend. So, for example, if we have orography beneath our rainfall field, we might want to take this into account, and it's very difficult. To do that, people often use geostatistical methods. However, these can have many parameters. They can be poor at estimating the extreme values and other rainfall statistics. However, they're straightforward to estimate, usually, and they are easily extended. So what we want to try is to improve these geostatistical methods using copulas, and for now we are trying to obtain appropriate local distributions for the rainfall, so that's the distribution within each core scale pixel. And the general approach is just based on viewing the downscaling problem as a bivariate distribution. So we have a core scale, we have a core scale value here. Is there a mouse here? Yeah, there is. We have a core scale value here. We fit a distribution and we take that value and simply transform it to its cumulative density. And we can use that to condition the copula, from which we then get an estimate of the distribution over the cumulative densities of the fine scale distribution. Then we can use the fine scale distribution to actually find the distribution of proper fine scale rainfall values. Of course, we understand that we need to also scale the marginals. We have done that already, but here we just fitted them as alpha stable distributions. So, as I mentioned, coarse and fine scale images are linked together using a bivariate distribution which is modeled with a copula. However, of course, the big question is always, how does this copula look? And as the title might have given away, it's very asymmetrical. As you can see here it's somewhat difficult. As you can see here, that there's no clear line in the middle and it bends downwards. And in fact, if we estimate this using the method of Durante et al., we can bootstrap these samples and find various estimates of the asymmetry. And we find indeed that for the very smallest scale, which is 4 pixels combined, we find that it's very moderately asymmetrical, and that as we add more and more pixels together, it becomes increasingly asymmetrical. And in fact, if you test for this using various significance tests, you find that all significance that we find is significant. All asymmetry that we find is significant. However, it can be somewhat minimal at times. Then, of course, the immediate question is, well, this is an asymmetrical copula. If you're aware of the field of copulas, you also know that there are very few tools to actually approximate this, and we use Liefre's method to do this. You can disregard the small part for now. Liefre's method is based on using symmetrical copulas to approximate an asymmetrical copula. To do this, they simply multiply various symmetrical copulas together, which, of course, when we would do this without any sort of function otherwise, we would find another symmetrical copula, and therefore we distort them using a function g. This can be an incredibly simple function. The most simple is a simple power function where the parameters sum to 1. Well, if we apply this, we can easily model a huge variety of various asymmetrical copulas. However, when we look at this method, we immediately end up with a question. Well, I can multiply multiple copulas together, but how many should I use? And which family should they be drawn from? And of course, what are all the parameters here? What value should I give to them? And of course, this is a difficult problem because the dimensionality, the number of parameters, can vary during the fitting. And to do this, we have used a method that's already been mentioned. The previous author, Dr. Ueda, called it birth-death Markov chain Monte Carlo. We call it a transdimensional Gibbs sampler. And it's simply a method that's highly effective at fitting various distributions, of a varying dimension. So when we fit, I can't see it on the screen. Okay, you can see it over there, luckily. So when we actually look at these copulas we have found, these empirical copulas, and attempt to fit them using the method I just described over a variety of scales, we find that the asymmetry is well approximated, because if we look at the range of scales, we see that the fitted copulas clearly move together with the empirical copulas, which are represented in black. However, we also see some fit problems, especially here in the top range, where the curves aren't really well estimated. This can be for a variety of reasons, but mainly we've attributed it for now due to the quite heavy autocorrelation within the data. We're going to be working on that in the future, but for now we found that this is a problem. And as I said, despite all these problems, it's a pretty decent fit. We're quite happy with it. Of course, looking at these images is interesting. However, maybe it's more interesting to look at the actual parameters and families we found. We found that for all the copulas we fit, for all the asymmetrical copulas we fit, we always use 2. We never need 3. So that's pleasant, less parameters. Furthermore, always all families we use are Gumbel copulas due to our method having an overwhelming preference for these copulas. And when we look at the parameters of these copulas, we immediately see that, yes, that's better. We immediately see that here we have our finest scale, so that's 1.2 kilometers square, and the coarser we go, the lower the parameters become. This is kind of expected. You expect the dependence to be suppressed, and also we more or less find something interesting. We see that only one parameter is actually being varied. The other parameter on this axis seems pretty stable. So that might suggest that there are less free parameters than there seem to be in the model. And we find similar estimates of the distortion parameters. Those are the power functions I just showed you. And we find that they're heavily correlated, which is completely expected. But again, we find a very, very strict trend. We find that they show a very interesting pattern where all of them seem to be following the same distributions. So that's also very interesting, and we hope to exploit these things in the future to be able to grant a very parsimonious interpolator. Of course, this is all very interesting, but at the end of the day we're interested in results and not so much interesting pictures. And to do this, we have looked at rainfall, simply a core scale image. We put our fine scale image underneath it, and we estimate empirical cumulative distribution functions. And then we do exactly the same. However, instead of using the empirical functions, we use the fitted asymmetrical copulas and compare it to a symmetrical copula. And if we do this, we find these functions, and of course the black line is the symmetrical copula. The black line is, of course, the empirical copula. Then the red line is the symmetrical copula, and the green line is the asymmetrical copula. And we can see that both of them approximate the empirical curve pretty well. We're pretty happy with this. What we're unfortunately not so happy with is that the asymmetrical copula already appears to give very, very limited advantages. It seems to be pretty similar. And indeed, if we... There should have been a few more images here, but alas, it doesn't show them. But if we show these over a variety of ranges, we find that for each of the rainfall values, we find that it approximates them quite well. However, we never really see a stunning difference between the asymmetrical copula and the symmetrical copula. And in fact, this point is driven home if we look at the root mean square error for both of these functions, and that we see that the asymmetrical copula usually does better. However, it's very limited. Usually, at max we see an advantage of maybe 0.1 of an increase, 0.01 of an increase of a decrease in root mean squared error. And if we compare these, we see that it always does pretty well. However, it's limited. So, as I mentioned, the asymmetrical copulas, they appear in rainfall downscaling. It's quite interesting, and we have attempted to fit them using Leuchter's method, and we find that they can always be approximated using two Gumbel copulas. Fitting them can thus be done through a transdimensional Gibbs sampler, which proves to be very effective at estimating these asymmetrical copulas. However, we also see that for now improvements are definitely necessary for some practical use, and maybe in the future they will, we can improve it a little bit. And that's actually our future research. We want to investigate the fitting more thoroughly, also expand it to time, and include actually a simple downscaling method so that we're no longer talking about some abstract interpolator, but actually have some nice rainfall imagery to show for it. That was more or less it. Pretty quick, I believe. Well, 13 minutes, not that quick.
Thank you, Matthias. So, any limits for your methods for, parameter values or special condition you can apply without any constraint, or?
But you can apply them without any constraint. I've so far not really run into limits, at least.
Okay.
Yes.
You.
Nobody asked. I've got one question. So
Sure.
At the beginning, you mentioned the geostatistical methods.
Mm-hmm.
You didn't mention that again. So,
Okay.
as far as I've seen, you did a spatial disaggregation.
Mm-hmm. Yeah.
And I have no idea how you want to do, using geostatistical methods, to do the spatial disaggregation. Can you elaborate on that? It's not an interpolation. You did just the spatial disaggregation of coarse scale to fine scale.
Yes.
So how is the geostatistical methods coming into play in that?
Well, in the future, we hope to include this copula-based framework into, for example, a sequential simulation, which would then be a geostatistical framework which uses our copula-based framework.
So not the interpolation, but the simulation.
Yeah, of course. I'm sorry. Maybe I was unclear. Yes.
Thank you.
Very good.
Yeah. I was just wondering, why do you need to use symmetrical copula? You can take something that's more flexible. Looking at your curves, I would have tried to use a Gompertz function, for instance, to simulate the non-symmetrical and the asymmetrical copula and minimize the error, basically the least squares between the two.
Could you repeat what kind of function would you use?
Gomberts.
I'm not familiar with it.
I mean, by taking an extra degree of freedom, basically, you may be able to do a better job. You're not stuck with copulas. You don't have to stay with the copula.
No, but well, this is of course this is my PhD project, and we started off with copulas, so it's kind of the momentum, I guess. I'm sorry, I have no proper defense against this, but there's always some other method, that you can use.
You don't need the defense. There is no attack.
Okay,
thanks. Okay. Zubeida?
Did you use two fixed points from your area, or did you study the relationship between the copula parameter and the entire distance?
Okay, could you repeat it because I didn't hear the first part?
So did you, in your presentation, did you choose two fixed points from the domains because you have an image?
Yes.
So how did you choose your two variables?
My core scale and my fine scale, simply by synthetically. What? No, am I wrong?
No, my question is about the parameter of the copula.
Mm-hmm.
Did you study its variability with the entire distance?
Okay. We simply use ergodic averaging where it was applicable, and in certain cases we simply found the most likely value. So that there's, we did not actually study the variability within as far as fitting the copula goes.
Okay. Okay, Martinez, thank you. So we can go ahead with the presentation of Hagitaksoy, stochastic modeling of Lake 1 water liver time series with gems and multiple friends.